geometry. We want to study algebraic varieties. We want to study their local rings, right? These are the fundamental objects. Now, these objects, they have the most desirable properties, right? You have all sorts of statement that says, all right, I take normalization, it's still finite, right? I take completion, it preserves reducedness, preserves always preserves normality. These sort of properties hold for these local rings. And we have the widest range of techniques, right? You always have all your commutative algebra techniques, like for Noetherian rings, right? Primary decomposition, maybe homological methods like taking resolutions, taking Tor. But specifically for algebraic varieties, you have analytic methods. And in characteristic zero, for characteristic zero algebraic varieties, you can also reduce modulo P. So you spread out the coefficient and then get varieties over finite fields or fields of characteristic P. So both of these methods are used, for example, to prove results like a Kodaira vanishing theorem algebraically. Well, on the other hand, you have these complete local rings that are not local rings of algebraic varieties. So you have power series factoring out something. These still arise naturally, right? If you have a ring of an algebraic variety, take its completion, it's complete. And also they are fundamental on their own, right? You use those in analytic geometry too. You have complete local ring of analytic variety. And by analytic, I mean either complex analytic or non-Archimedean. So these are super interesting too, right? They retain a vast majority of desirable properties, right? If I have a complete local ring, I have a finite type algebra over it, then, for example, the normalization is still finite. They allow most of the techniques, such as I said, algebra techniques, right? Like Noetherian rings, the traditional stuff, but not all of them. So you cannot technically use analytic methods, right, for a complete local ring that has like non-convergent power series. You cannot reduce modulo P because you have infinitely many coefficients in your power series ring. But I mean, even if you're not interested in that, in the abstract theory of commutative algebra, even if you just want to focus on varieties, the complete local rings are still very useful in the study of varieties. So in the traditional proof of resolution of singularities by Hironaka a few decades ago, 4 decades ago, I guess. No. 6 decades ago. He used complete local rings, if not broader class of rings, to make the inductive proof, work better, or maybe it's in some sense essential, right? Because you want to use the induction and the invariance of the complete local rings. And they also can be used to prove some boundedness result, some abstract boundedness result. So basically, if you can prove some statement holds for a complete local ring, then you automatically get some potentially very weak, but still non-trivial boundedness result on varieties. So the principle here is that if you have a situation of algebraic varieties that goes like worse and worse, described by certain polynomials, you can amalgate all these polynomials together, put all the coefficients together, and take a somewhat, non-standard limit. That way, you will get a polynomial, a power series in a larger field. You get a power series because the degree of the polynomials may go larger and larger, right? So if you know it about power series, then you get some sort of boundedness over polynomials because you cannot have worse and worse polynomials because their ultra limit, whatever that is, will be a bad power series. So you have this duality where you have these most fundamental things, and there's slightly less fundamental things. And the problem is the statements proved for the first class of rings are sometimes not available for the second class. So Kodaly vanishing theorem is the example I mentioned, was only recently proved for complete local rings because these methods, analytic methods, and reduction modulo P are not available there for complete local rings. So now this is our motivation. And what is our goal? So our goal is to approximate complete local rings with local rings of algebraic varieties. So if a complete local ring is the completion of a local ring of an algebraic variety, then many things can be said about that ring from that algebraic variety or that local ring. Of course, this is not true for many complete local rings, right? Most complete local rings are not completions of local rings of algebraic varieties. However, they can still be approximated, and in many ways. So in the literature, all right, okay, so we want to generalize known results for varieties to complete local rings by approximation. So in the literature, people have done this, right? People want to do this. So an example is in Hoxton and Hunicke's book. They studied tight closure in characteristic 0. So tight closure is an operation in characteristic P. And in characteristic 0, you want to define tight closure via reduction modulo P. But that is not available for complete local rings. However, you can approximate them with local rings of algebraic varieties, have tight closures in those approximations, and then take some sort of limit or co-limit or whatever. So this is, in fact, very close to the approach we are taking in this paper, even though we only found out after we started. This is not like entirely new because it's a very natural thought that many commutative algebras might have considered. And so another example is Kodaly vanishing theorem I mentioned a few times, again by approximation. They also appear occasionally somewhere else, right? I have seen those in, for example, Gaber's work on alterations, regular alterations. I've seen this in De Jong and Brian Conrad's work on algebraic spaces, arcing approximation, like sporadically. And our goal is to establish a framework that will be more systematic and allow folks to work from what we set up. We also have our major directions of application that are new. So for me, I was thinking about singularities in characteristic 0. As I mentioned, this is the field where the difference is most drastic, right? For algebraic varieties, you have a complex analytic methods and you have reduction modulo P, but those are not available for complete local rings. Definitely, you can say a lot about approximation in characteristic P and mixed characteristic as well. However, many of the known methods in those characteristics are already available for complete local rings. So we might not immediately get that many applications, but maybe some. So this is the major application I have in my mind. And Shiji and Bogdan, they were considering Adel cohomology. And again, many results for Adel cohomology are only known for algebraic varieties, such as decomposition theorem. So we want to generalize this decomposition theorem to complete local rings, and that will be new. Sorry, I didn't have that. here. So
Shiji, how
that's
about
another
other
direction.
vanishing theorems? How about other vanishing theorem, the generalized Clayura's vanishing theorem, like a Nakano vanishing theorem or other types of vanishing theory, the Kaumata feedback?
Yeah, so good question. So two things can be done here. One is that you use the standard way to deduce those theorems from Kodala vanishing theorems. If you're working with, for example, Nadel's vanishing theorem, right, about multiply ideals.
Yeah.
For the Akiyama Nakano, it's not clear. And our method should shed some light in that direction because it's about higher differentials, right?
Yeah.
And the relative versions, as you can see later, that because this framework is more systematic, we should be able to say something.
Okay. Good.
Yeah. Great. So Adult homology 2 and singularity is characteristic 0. Right. Okay, great. So we have a sample application here for you to see, right? So this is you know, about singularities in characteristic 0. So let's say we have a local ring of an algebraic verity in characteristic 0. We have a regular element, so or a non-zero divisor if you prefer. This is basically saying I have a germ of a verity and a Cartier divisor. So if the Cartier divisor, if A over AA has rational or Dubois singularities, then so does A. Right, so this result is known. It's for the rational singularity part, it's 78. For the Dubois singularities, it's relatively recent in 2016. And our method of application tells us that because we know it's true for local rings of algebraic verities, we can actually deduce it for all complete local rings of equal characteristic theorem. And for the experts, right, this is actually true for all quasi-excellent local rings. So we want to point out that if you don't know what this is, basically that's a class of local rings studied in EGA, and they axiomatically captures most of the desirable properties of complete local rings and local rings of algebraic verities. And to deduce quasi-excellent local rings from complete local rings, this is pretty standard. You just need to base change the completion. So from here to here, it's nothing new. It's folks have been doing for all these times. But from the algebraic verities to the complete local rings, is something that we will systematically capture instead of the sporadic, the occasional usage in all those literature papers. Right. So I want to also point out that the spirit of our result is that you could ignore what the original proof is. You can ignore how the original proof went, which is formally approximate the complete local rings to reduce the result to the result for algebraic verities. It is very possible that if you actually read the proof for algebraic verities and understand that proof, maybe it also works for complete local rings. However, this is, a lot of burden for you, right? You have to actually understand that proof. You have to actually check that everything works. And if they have a reference that also only assumes it's an algebraic verity, then you need to check that that reference also works, etc., etc. So it's better that you can just do it formally, right? From the case of algebraic verities. And this is also the route that is taken already in like EGA and SGA, is that the first thing they will do is to reduce the problem to a ring finite type over Z for many of the propositions. Maybe unnecessary, maybe not, but it's extremely convenient. So the point I want to make here is that we do not necessarily claim full originality for some of these corollaries, right? Because these proofs may be adaptable already, right? But the point is, with our approximation scheme, approximation framework, you can use minimal effort to get the result. So I want to stop here if you have any questions for a moment. All right, let's see how much time we have used. All right, great. So this is our one sample application. Next, I will list some applications that is already being considered or being considered. So rational singularity in Dubois, I just mentioned. You can also consider singularities in the minimal modal program, such as KLT and LC, which is Kawamata log canonical, Kawamata log terminal, log canonical. Whatever they are, again, our framework will not require you too much understanding of these. You can formally deduce the result back to the verity case. You just need to know maybe its definition, some of its characterizations, and then you can do formal stuff. More, multiplier and test ideals. So multiplier ideals, some sort of numerical or quantitative measure of KLT. Same for discrepancies, right? And test ideals, what are those, right? So if you don't know what these are, it's fine. But in characteristic 0, we usually consider Bickel-Macaulay test ideals. By usually, I mean just in the recent few years, because Bickel-Macaulay algebras is a recently new focus in competitive algebra, partly due to the fact that their existence are not so easy. Anyway, so these are some recent trends in competitive algebra. If you're not familiar with, just think about multiplier ideals and KLT and LC singularities. So for the experts, right, Bickel-Macaulay algebras in characteristic P is very easily constructed, has some canonical choices, and detect a lot of singularities in characteristic P, right? In characteristic 0, what you want to do is you take reduction modulo P, and you get Bickel-Macaulay algebras of these reductions, and then combine together yn ultra product. So this is some work by Skeltons and then work by Yamaguchi that tells you that Bickel-Macaulay algebras in characteristic 0 that comes from reduction modulo P are very good. They are very nice. But again, this is not available for complete local rings, but we can do something with our approximation. Right, so we can generalize these constructions for varieties to complete local rings. And I want to mention that there will be potentially a lot of synergy with work by me and Takumi on minimal modal program for excellent schemes over Q. So again, if you don't know what an excellent scheme is, just imagine a finite type scheme over a complete local ring, right? So the minimal modal program is a very useful tool in algebra geometry, right? A lot of work has been done. The minimal modal program with scaling established by Bierkar, Cassini, Heiken, and Xu. Heiken and it's always hard to remember the names. BCHM, Bierkar, Cassini, Heiken, and yeah, okay, great. Sorry about that. But basically, there are subsequent works on like algebraic spaces, analytic spaces. The main difficulty is that even the most basic Kodaly vanishing theorem is not available for complete local rings. Since Takumi established that for complete local rings, we can just adapt methods by Cassini and Latich to establish, the minimal modal program to some extent for excellent schemes over Q. Now, the point is, when applying the minimal modal program, you need to check like intermediate steps satisfy certain properties, right? For example, it preserves KLT, right? And you can potentially check some of them properties with our approximation method without knowing how the original proof works. Because, for example, the canonical bundle formula depends on some analytic stuff, right? The original proof. We do not know without a serious, read-through that whether or not they can be adapted to complete local rings. But maybe with our approximation method, we can do a lot of things. So the point is, this will be a framework that is capable of producing new results with less effort, and some of them maybe will be the only known way to do it. So, for example, the Baker-Macaulay algebras, I'm not aware of any other way to construct a nice enough Baker-Macaulay algebras other than using our approximation method, right? And I have no idea how I would do that if you ask, because the original method is by reduction modulo P. All right, so in the adult homology direction, you have the composition theorem, right? I want to generalize that to complete local rings. But also, another thing we can do, again, is to generalize these to structures that have complete local rings. Right? If I have an analytic space, I can take its complete local ring. And then if it holds over that complete local ring, then by some sort of flat descent principle or, check your statement at every term principle, you can generalize it to other geometric objects. And what they have in their mind is rigid analytic spaces. Some part of the theorem cannot be generalized to rigid analytic spaces. That's because it's just false. But for the parts that we hope to generalize, we want to get it from this approximation framework so that we won't run into trouble that some statements because original in the BBD paper again is by reduction modulo P. Right. So hopefully this gives you an overview of what we are aiming to do, right? And there's no way that I can give an exhaustive list of the applications because, as I said, this is just about formally approximate the complete local rings with the local rings of algebra varieties. So any result about algebra varieties you can think of, you can possibly think of how to do it here, right? And there's no way I can list all the results in algebra geometry, right? So, and of course, some of them we're not able to immediately see how to do it right now. So those include local cohomology and Frobenius in characteristic P. For the local cohomology part, the local cohomology modules, they are generally not finitely generated modules. They're not finite type objects. They may be finite, holonomic D modules, but those are still currently beyond our reach. Another thing is the Frobenius map in characteristic P. So this is very interesting. However, in characteristic P, most of the methods are already available for complete local rings. So we don't see immediately if we can get an application out of it. The formal approximation still works pretty fine. And so on. So anything you can think of, if you know it for algebra varieties and you want it to be true for complete local rings, for excellent rings, maybe our method can be of some help. Even if our method may not be able to immediately get it, for example, for local cohomology, it can serve as a very helpful tool. So just imagine your like EGA for limit argument. It's pretty useful. Sometimes folks just ignore it, but it's actually essential in some of the proofs. All right.
Yeah.
So
may I ask a question? So do you have some examples like the results easier to prove over complete local ring, but not the general algebraic varieties? Like backwards, instead of saying, we have some results on algebraic variety, you may expect similar result on complete local ring. But backwards, do we have any results that's holds true on complete local ring, and we don't know yet it's true on, algebraic variety in general.
So I would say this will be very hard to find, and the reason is for every algebraic variety, as I've described here, you can take the complete local ring of their local rings. You can take the completion of their local rings, and that completion map is a faithfully flat ring map. Is a regular ring map. It preserves most of the properties you want, right? So if you want to check something over an algebraic variety, it's easier to just straight go to the completion and then say by faithful flat descent, the original result is also true.
Yeah. So in other words, you're saying it's here easier to prove a result on the complete local ring. I mean, sometimes not, right? Let's
Well,
say, for
it
example,
is true,
yeah.
but okay. So sometimes it's easier to prove it over a complete local ring because, for example, if your result involves an induction, right? Maybe the inductive, anytime any result in mathematics that involves induction, it could be easier to prove a stronger statement. That's why sometimes it's easier to prove the results over complete local rings. Because they're strictly stronger than your original statement, and that may help in induction.
Good.
So you can, in those induction statements, sometimes the first step you do is take an obviously stronger statement than the original one, so that you can proceed. Right. So, yeah, generally speaking, any homological or singularity properties, is preserved by this base change to complete local ring. Right. Not all, but most. Yeah. All right. So up until now, this is the framework. This is, our principle or our idea that we should, not need to repeat so much effort already being done for algebraic varieties. We should just be able to deduce it formally, and also for some results, decomposition theorem, Baker-Markov algebras, and the Kodala vanishing theorem. There's no way known that we can do it without approximation, because the construction for algebraic varieties is not replicable. Right, so the rest of this talk, I will go through some of the technical parts of our framework. And, if you're not familiar with maybe this topic already, it could be too fast. But yeah, I mean, I of course, I mean, because this, it's a whole like load of things, right? So I'll go through it relatively quickly, and maybe later after you share the video, you can check back the slides. So because there's no way I can fix a speed that is good for everyone, I don't think. We'll just see which part you want, you have questions, and we'll adjust my speed according to that. So the rest will be relatively technical, but I will keep it relatively simple by focusing on the power series ring, where you have a field of characteristic 0. The approximation argument is valid in all characteristics with different applications, but most in characteristic 0, again, by the reason I explained before. For the algebraic variety that gives this complete local ring, as I said, some complete local rings are relatively simple because they are completions of local ring of varieties. Here, you just take a local ring of the affine space at the origin, and R is the completion of R0, right? By Popescu's theorem or Artin-Popescu's theorem, R is the direct limit of a system of smooth R0 algebras. If you don't know about it, ignore the sentence. Just believe it. The point is we want to write R to be the filtered colimit of Ri, where each Ri is a local ring of a smooth variety over K. In fact, the variety is smooth over the affine space. So these Ris, they are local rings of varieties. and R is the direct limit. Okay, so this is our situation. You have this complete local ring R, power series ring, and its direct limit of local ring of Smith varieties. Let's say you have a finite type R scheme over, let's denote it by X, and you want to approximate it. So classical work in the EGA tells us that X is the base change of a finite type Ri scheme for some I. So you can sort of descend that X onto some of these Ris. And Xi is not exactly an algebra variety because Ri is local, but it's sort of a germ of an algebra variety. And this Xi is unique up to passing to a larger index. And what does this mean explicitly? If I have an Xi over Ri that defines X, and an Xj over some Rj that also defines X, then after base change to a larger index, after base change to Rk for some larger k, Xi and Xj are isomorphic, compatibly with X. If X is flat or smooth or proper over R, then Xi is flat or smooth or proper over Ri after you pass to larger indices. So these are all classical works, right? So, and these, what the point of these is that they do not require a special property that these Ri are regular, right? They are smooth varieties. This is true for any direct limit of rings or for safety Noetherian rings, right? That you can approximate finite type things, preserves these properties. But the properties you preserve are all relative properties. So if X is flat over R, then Xi is flat over Ri for large I. If X is smooth over R, then Xi is smooth over Ri for large I. It doesn't say anything about the absolute properties of X, right? So if X is irregular, EGA does not tell you if or not these Xi's are regular for large I. Again, there's a difference between the scheme X absolutely being regular and it's relatively being smooth over R, right? You can have a map of two smooth varieties that is not regular, that is not smooth. In other words, you have a map between smooth varieties. This is not locally a submersion, right? You can have just like a degree, a covering of P1 by a curve, right? By a smooth curve. That map itself is not smooth, despite the curve and P1 both being regular. So EGA will not tell you if you get regular Xi's if you start with a regular X. But our framework, our observation will tell you that you're actually fine in your situation. And the reason is because, again, the special property that these Ri are regular did not exactly need to be as good as regular. The key property that we want is that Ri to R is a local complete intersection map. So what does this mean? Well, there's a formal definition, right? But concretely, right, in our situation, this means that our Ri hat to R is surjective and its kernel is generated by a regular sequence. And this is true for any surjective map between regular local rings. If you have a surjective map, or if you have an ideal in a regular local ring that also defines a regular local ring, then that ideal is generated by a regular sequence. So you can view spec R as a complete intersection in the spec of the completion of Ri. Right, so this is our observation about the general framework for general direct limit of Noetherian rings. Okay, so now our observation is that R is direct limit of those Ri's, and these maps Ri to R are local complete intersection maps. Finite type R scheme X base change from a finite type RS scheme Xi. So our key lemma is that, all right, we know Ri to R is local complete intersection, but what about x to xi, right? And the technical term that we want to use here is that xi and r, they are Tor independent over ri. So if you know what Tor independence is, you can expect a lot of good things already from the sentence, right? Basically, we're just saying, okay, if I take the tensor product of xi and r over ri, then the tensor product captures everything. There's no higher Tor groups, or that the tensor product is already derived. But if you're not familiar with Tor independence, concretely, this just means that irregular sequence that defines spec R is spec Ri hat. Remember, Ri hat to R is a surjective map whose ideal is generated by a regular sequence. And I'm essentially saying that this regular sequence remains a regular sequence in Xi, while technically it's in the base change to the completion. So if you ignore that completion, I'm just saying that X is a complete intersection in Xi. For it to be technically correct, I do need to take that completion. Yeah, so that's the point of this Tor independence geometrically. And now you're happy because when X is proper over R, this closed subscheme X, it actually contains all closed points of the Xi prime because we're working over a local ring, right? So if, for example, X is regular or reduced or normal or Gordian, etc., so is Xi prime. And that is because X is a complete intersection in Xi prime. So remember, you have all these propositions in your commutative algebra textbook that says, okay, I have a local ring, I have a regular element, I factor out that element. A over AA is normal, then A is normal. A over AA is reduced, then A is reduced. And because of that, if X is regular, because it's a complete intersection, then so is Xi prime. You are fine because you have all closed points, you capture all the information, right? When X is not proper, some extra work needs to be done, usually by doing a good enough compactification, right? Just take any compactification and then make it reduced, or take a compactification and make it regular. This is standard in algebra geometry, right? You have an affine variety, you embed into a projective variety, and you take a resolution that is isomorphic over the original variety by Hylonakas result. So you can do it for non-proper stuff as well. So this explains why we have this, right? The point is these local rings, they're not arbitrary local rings. They are local rings so that Ri to R are local complete intersections. And this will give you Tor independence, and therefore X is sort of complete intersection in those Xi prime. And therefore you can get the property from X back to Xi prime, and then also back to Xi just by flat descent. So yeah, if you're not already familiar with this gadget of like completion and flat descent, you can simply ignore these primes. Just imagine X is the complete intersection in Xi, even if it's technically not. This is very standard. This part is sort of new, is what we want to exploit. Right, so that's the technical core of, or maybe you can call it a starting point, or maybe kind of the technical core for our approximation system. And of course, you don't want to just do it for the schemes X. You can do it for all sorts of objects, coherent sheaves, a bounded coherent object in derived category, divisors, finite time morphisms. Right? So by a very similar recipe. F will be Tor independent. The cohomological modules of M will be Tor independent. The divisor, well, some work needs to be done, right? The weight divisors, they are defined as formal combination of closed subschemes. For every closed subscheme, it's just another X with a different name. And for it to stay a weight divisor, you need some sort of normality being preserved for the whole X, and you need like integrality to be preserved for the prime divisors, and you need maybe other properties like being S1. I will omit the technical details, but basically because of these properties being preserved, a divisor on X will be defined by a divisor on Xi in a in a neat sense, right? You'll have good base change properties regarding, for example, the ideal sheaf of that divisor, because remember you're taking formal combinations. There are some things to take care of. And of course, we want to approximate morphism schemes, right? Some may argue that this is actually more fundamental than this, which I will agree. Approximating a single X is the same as approximating the map from X to spec R, which is a special case of this. Right, so just again, want to repeat the caveat is that you always need this, this sort of finite type, situation, right? If you are approximating, for example, local cohomology modules, there might be problems because they are not finally generated modules. So just to keep in mind that this is definitely not invincible. You have some problems, but it's already good for a very broad, a huge variety of questions. Okay, so this is our setup finished. I would say, let's go ahead and see how this setup can be applied to give applications or sample application, what I mentioned before, had this result regarding rational singularities. How do we use our approximation scheme to tackle this problem? So the thing is, by Cohen structure theorem, the complete local ring A is a finite R algebra for a suitable N. So remember, our R is a power series ring with N variables of some field, and that N and that field, they are arbitrary. So by Cohen structure theorem, A is a finite R algebra if you choose a suitable K and N. Right, now X, take it to be spec A, so A is the base change of a finite R algebra AI. It's automatically local. This is just a small technical point. Feel free to ignore this part, right? But the point is that it reduces to some problem of local rings of algebraic varieties, right? This is both of these are local rings of algebraic varieties. Because A is the colimit of those AI, the element A comes from an element AI, right? So these are pretty standard, but the first sort of application of our new technique is that if we enlarge I, then this AI is a regular element. So why is this true? Well, strictly speaking, it's an immediate consequence from Tor independence. If you still do not want to think about Tor independence, which many people do, and I do, then this is just about interchanging order of regular sequences. So just imagine that A is defined by a regular sequence in AI. So the fact that A is a regular element in A, just saying that, okay, this regular sequence that defines this ideal plus this new element A is still a whole regular sequence. So now you have a long regular sequence. You take its last element, then that last element is a regular element because regular sequences, you can interchange their order. So, right, so abstractly Tor independence gives us this, but more concretely, it's just interchanging the order of regular elements in the regular sequence. Right, so now we have this proposition A or A over AA has rational singularities if and only if AI or AI over, sorry, typo here, it should be AI. So I will use the annotate. Right? Okay. Right. So if and only if AI over AI has rational singularities for large I. So this kind of proposition will be sort of the key to deducing these results, right? We want propositions like this. The complete local ring has some property if and only if those local rings of algebraic varieties have the same property, right? Now, this proposition reduces the theorem from A to each of those AIs, which are local rings of varieties, and therefore the result is no. So this is how we get our applications for these type of theorems. To construct complete local rings, to construct big Kolmogorov algebras for complete local rings, you need more than that, right? To prove decomposition theorems, you have your own technical obstructions, but many of the intermediate results will look like this. All right, so so I still have some time, so otherwise I could have stopped here, but let's just quickly go through how this proposition is proved to give you some confidence on the versatility of our argument. So, some sanity check, A over AA is normal, and this so is A, so in particular it's integral domain. We only prove the proposition for A because it's the same for A over AA. How do you check if something has rational singularities? Well, you take a resolution singularities, right? The point is now we can approximate the resolution singularities. By EGA4, G is the base range of proper morphism. Phi Tor independence, as we mentioned before, Y is essentially a complete intersection in YI, and X is essentially a complete intersection in XI, and therefore Y is regular and X is normal for large I. And also using the Tor independence, the complete intersection thing, you can check the dimensions, and therefore GI is birational, right? It's always surjective, again, by general principle. It's birational because the dimensions are the same here, and therefore, because you're factoring out the irregular sequence of same length, dimension still the same, so you're birational. And therefore, GI is a resolution singularities. Right? So you can approximate resolution singularities by our argument. You can also approximate, for example, blow up. You can approximate certain other constructions because they're characterized by these properties, regular, birational, including log resolutions as well for divisors pairs. So, right, classically, you define rational singularity as the higher cohomology of the structure sheet, or resolution being 0. And now Tor independence kicks in again, right? Generally, what you would have is the total push forward or the total cohomology in the derived category satisfy a derived base change. But because everything is Tor independent, including the scheme itself and the cohomological modules, you have this. This needs some work, but those are mostly formal, like dimension shifting in from A equals to the top member down to bottom. And this gives you that this thing is 0 if and only if these are 0 for large I. And again, this is available in EGA4. As soon as you have this formula, where a finite type module is the base change of these finite type modules, you know that the module is 0 if and only if these finite type modules are 0 for large I. So this part and this part are classical. They are known far ahead, far before. But this part where you can retain the good properties of the morphous and you can separate comolecular modules are sort of new observations from our framework. All right, so okay, so that concludes the proof for our sample result. And it can do a lot of things. You can also do like canonical modules, canonical divisors, which will give you an alternative proof of the relative Kodala vanishing theorem for complete local rings. You can also probably do it for higher differentials. For Akizuki Nakayama, you can do it for other constructions too, right? So it's very versatile. I will never have enough time to tell you what are all the potential applications. You do need to check individually if some of them works or not, but these checks will require relatively minimal effort comparing to, so basically you just need to check these notions themselves are compatible or not. And once you do that, you are fine in the future for all results regarding these notions. You do not need to check individual proofs, which is great. Right. So that question?
Yeah. Those results are in characteristic 0, right?
That's right. So in characteristic P, you could have something else that I'll mention next.
I see.
Yeah, so these are in characteristic 0 because you need that result to be known for local rings.
The resolution of singularity at least is the one result.
Also resolution of singularity is only available in characteristic 0. Yes, because these are known algebraic varieties of characteristic 0, you can deduce it for local rings. All right, great. So let's go to.
So here you can see the rational singularities. KLT singularities are rational. I guess KLT singularity, the result if you replace rational by KLT is still true, right?
Yes. And
how about
it follows the same pattern.
How about that?
You take a KLT singularity and you have the same proposition here.
How about
and the reason is because it's because you take a log resolution, and it will keep a log resolution, and prime divisors will keep prime divisors. Discrepancies will be the same. You just check if the discrepancies are greater than -1.
That's saying even we talk about log canonical is still true, right?
Log canonical is still true. You can cook up your own thing. You can say something is nice if it's always the discrepancies are greater than maybe the cubic root of pi, and it will still be true because everything is just preserved. And you can even do it for multiplier ideals again by this. You can replace the homology of structure sheaf by that of that resolution, that divisor, and you will get that the multiplier ideals are preserved too.
Great, sounds great.
Yeah. So to conclude, I'll just mention this alternative situation in characteristic P very quickly. So here it's very different because you have method in characteristic P already available for complete local rings. But I have this strange object, which is the base change of a power series ring to an algebraic closure of your field. Now, if you consider a finite extension, then this tensor product is just another power series ring. So how can we approximate finite type objects over this guy with finite type objects over these power series rings? And it will still have that these maps are LCI in a well-defined sense. But the difficulty here is that this ring is very bad. This ring is not excellent. This ring does not have those desirable properties. So if a reduced finite type algebra, if you have a reduced finite R star algebra, take its completion or takes the base change to our star hat, it's generally no longer reduced. So this is a alternative situation in characteristic P. If you're more interested in characteristic P, this is interesting to think about. Okay. So I'll end here. Thanks for your attention.